Challenge, please.
Dear judges and fellow competitors, we would like to Lavoisier would like to challenge problem number 10, droplet explosion.
What's wrong? There's a sign.
We will accept the challenge.
Please write down your name.
I would like to move on to my report.
Please.
Hello, distinguished judges and competitors. I'm Jason from teaming, and today I'm bringing problem number 10, droplet explosion. First, let's look at our problem statement. When a drop of water mixture like water alcohol is deposited on the surface of a hydrophobic liquid like vegetable oil, the resulting drop may sometimes fragment into smaller droplets. Investigate the parameters that affect the fragmentation and the size of the final droplets. So in here we can see that we should use water mixture and hydrophobic liquid as our surface. And what we focus on is the size of the final droplets, and we do talk about the fragmentation here. So for our experiment method, we mix different alcohol with water, like in the problem statement, in different concentration, and we place it on the surface of a layer of rapeseed oil, which is hydrophobic. And we wait until the droplets to come to a stable status while recording the reaction of the droplets. So we consider the whole layer of oil flat here, and all the mixture ideal, which food coloring we add to observe does not affect the solution. And we also consider the whole water mixture droplet drop onto the surface in a very short time, which we couldn't manage to drop all the mixture in just a little second. So here's our observation video. We can see that a thin layer of oil spread onto the thin layer of mixture spread onto the surface because before it starts to fragment into smaller droplets, which I'll discuss later. So in our theory, when we think that when a water mixture droplet touches the surface of oil, alcohol in the water mixture tends to spread on the whole surface in a very short time, which we saw in the first state. And then the water will spread a little because the flow that the solute, which is the alcohol, gives. as we can see, this circle is the alcohol which spreads and the water remains in the center. Then, when the thin layer of alcohol evaporates, we think that the rest of the liquid tends to fill in the holes, like in the picture shows. And the mixture will then form into humps at the rim of the hole, like here, and which causes the circular curling of the droplet array. So like we can see here, starting to evaporate, and there's our circular curling. The droplets will then be generated periodically in the linear curling phase, like here's the circular curling phase, and then move on to the linear curling phase. At last, a regular 2D structure will form over the entire water surface by rhythmical shrinking and expanding motion, and remains for a relatively long time as a stable pattern. So as we can see, it starts to evaporate and then curling, the linear curling state, and then it stays at that status for a rather long time than all the states before. So the form of a hump, we think, is a conclusion of both liquid flow and dewetting, which the flow brings it up and dewetting brings it down. So evaporation creates the flow on the surface, which gives the mixture a cohesion force to form this flow. The electron mixture will be given an opposite force like for dewetting, so the next hump will be formed in the linear curling status periodically. So, as we said in our theory, so we chose these parameters for first, is the different kind of alcohol, which we think there's a different surface tension between them, and a concentration of the water mixture, which we analyze if water or alcohol has a major impact in that. And at last, it's the size of the Petri dish, which is the area of the oil, which the area it can expand onto. So this is our first experiment setup. We use an 11 centimeter diameter Petri dish, 100% rapeseed oil, which we use in constant thickness, and blue food coloring. So for our measurement, we photograph the last status. Oh, we actually record the whole process, but we use the last status picture to calculate the rate of each droplet comparing with the size of the Petri dish. So we get the final size of each droplet. So first, we use ethanol as our alcohol. We mix 95-degree ethanol with water in both 75%, 50%, 25% concentration, and place on 20 milliliters of oil, which all result in no reaction like the picture here. So then we move on to our next alcohol, which is isopropyl. We mix isopropyl alcohol with water in 75%, 50%, and 25%. And we actually use other concentrations, which we will talk about later, but these are just the main we discussed about. And we place on 20 milliliters of oil as we do in the last state. So for our 75% concentration, we yield the result like this. For 50%, we have a result like this. And the exact size of the droplets on the dish is like this. We can see that below the concentration of 37.5, there's barely no reaction of all the oil we chose to use. And the smallest droplets in the inner circle appears in 50%, and the smallest on the outer circle appears in 75%, which is the outside circle and the inside circle here. So then we move on to our experiment of 25% isopropyl alcohol, which have no reaction, which we just said. So next we use 15 times 10 centimeter glass piece, which is a larger area, which we place the same thickness on it and use the same setup. And here's our video, which we result in like this at last, which we can see the 75% have a large portion of liquid stuck in the middle of the area. We see that 75% mixture has a higher hydrophobicity, which sinks into the surface, and only the mixture that's spread briefly divided into small droplets on the outer circle, which we can see here at the outside. And we think it's that because the force of fragmentation is smaller than gravity. However, the small droplets of the 75% mixture is smaller than the 50% mixture, which we cannot show clearly at the side of our picture. So here is a graph which we talk about the sink into a surface. So when you drop it on the surface, it collides into the shape like this, and then it sinks into the oil because of its hydrophobicity. Then we chose to do 50% concentration, and we have two kinds of result, which is it sinks into a surface, and it results like this, or it spreads onto a surface without sinking, and it yields a result like this. So we think that the 50% mixture also sinks into a surface as we observe, but the sinking velocity and depth is smaller than the 75% mixture, which there are two situations which we see here. So if it's spread before sinking, the fragmentation process is towards the center and it fragments faster. If it sinks into a surface, the fragmentation tends to spread towards the outer circle and it's slower. However, both of them, all the mother droplets in the center disappear at the last state. So then it's our 25% isopropyl alcohol experiment. So we can see there is still no reaction. Then is our exact size of the droplets on the glass. So we can see that like the experiment before, when the concentration is lower than 37.5%, there's barely no reaction. And the smallest droplets on 50% and 75% is still in the inner circle and outer circle. So if the fragmentation spreads toward the center, we see that the bigger droplets tends to stay on the outside, which we think there might be because of the fragmentation and also some collision of each small droplet, which they tend to stuck together at last. Then if it spreads towards the outer circle, the bigger droplets tend to leave on the inside, and the minimum concentration for spreading we think is 37.5%. So as we can see, for the surface tension, concentration, and the area of the oil, we think only concentration affects the size of the droplets. But if for effect of the fragmentation, the surface tension only triggers the first state, which is the alcohol spreads onto the whole surface for the droplets to fragment, and both of them for the area, it only affects the fragmentation on the side of which I said might there be a collision between the small droplets because the area of my plate. So as I move on to my conclusion, we see that different sizes of droplets form because of different surface tension between the mixture and the oil. We think that because ethanol has a higher surface tension than isopropyl alcohol, so it cannot successfully separate from water, which onto the whole surface to trigger the first state. Then we think that a high rate of water in the mixture also makes the alcohol harder to spread onto the surface, which is why 25% of isopropyl alcohol mixture have no reaction. Comparing 50% and 75% mixture of isopropyl alcohol mixture, it shows that all mixture of 50% mixture can spread onto the surface, but a major portion of the 75% remains in the center of the surface, which we just talked about the reason. And last is, I conclude some key factors of our fragmentation, which we have a fast spread at the medium concentration, and we got smaller droplets if we increase the concentration of our alcohol mixture. And some key factor of fragmentation is you need a smaller surface tension of your mixture, your solute, a medium concentration to provide a whole spread, and the water mixtures to be hydrophobicity and the lipophobicity of our surface. Thank you for listening.
Okay, please turn to page 4, please. I want to see the food coloring. Do you have any data for establish that food coloring does not affect this phenomenon?
We add a little only, so we
A little. How much?
We use, like we said in our experiment, we use 25 milliliters, but we only add a drop of food coloring. So
A drop of food, how much a drop of food coloring?
I think it's smaller than like 0.1 milliliters. So it's we
You
just ignore that.
Okay. Please turn page 4 observation video. Do you have you have your own observation video? I think this is from some reference.
These are
I do not see
these are my videos.
I cannot clearly see the fragmentation
Here on the side. And as I said in my theory before, this is my experiment. So you can see
page 8. Please. Okay, so in page 8 you said that it may have some holes, but this phenomenon is basically bursting. So it's droplet explosion. It does explode. So this I don't know what this means. It's
evaporation.
You said liquids tend to fill the holes. What holes? Okay.
The evaporation. Because the alcohol, thin layer of alcohol evaporates, so there will be holes on the surface.
Okay. Please turn to page 10, please. No, sorry, page 13. Did you measure the surface tension? Have any data for surface tension?
No, I just found the data from for the liquid.
Okay. Thank you.
Opponent, please.
dear judges and fellow competitors, I'm the leader of Team LaFlocke. I'm posing problem number 10, droplet explosion. So this is a problem statement. When a drop of water mixture is disposed on the surface of a hydrophobic liquid, for example, vegetable oil, the resulting drop may sometimes fragment into smaller droplets. Investigate the parameters that affect the fragmentation and the size of the final droplet. We now focus on two main points: relevant parameters and the effect on fragmentation and the size of the final droplet. So I'll make some conclusion for reporter. So the phenomenon is the syringe. They use syringe to dispose the water, alcohol or water IPA mixture on oil. Then is the theory, which is the alcohol evaporation, liquid flow, the wetting cause formation of pumps. For their experiments, they measure the final size, per dish size, concentration of alcohol and IPA. For the reporter pros and cons, for well-characterized parameters, clear illustration, and maybe 3 parameters. Okay, moving on to pros and cons. For cons, they have unpersuasive theory, non-intuitive explanation, and does not roughly explain the phenomenon, lack of error analysis, and problematic experiment. So we're now moving on to the point we will discuss. So first, we'll talk about the theory, whether water mixture and hydrophobic liquid are necessary, which is in the problem statement, and also the flow of hydrophobic liquid under the surfaces. Then with some fragmentation, why does it form such a fragmentation? And the droplets size I observed in your video, which is not uniform, and some dissolve when you dispose the water mixture on the oil. Will it dissolve? And with some measurement of the error of injected practice and heritage size. For experiment, we'll talk about some effect of dye, temperature, and volume of the initial drop. Then we'll talk about more. We will talk more about the conclusion. Okay, I want to move on to the discussion. So can you answer me the first question? Whether water mixture and hydrophobic liquid are necessary?
I think they do because, like I said, when I chose to use only water, there's no reaction. So water mixture should be necessary. I also choose to do a higher concentration, but it will just sink. So I cannot observe if there's the spread or not. So I can't tell you when it's 100% if it's necessary.
So if some non-hydrophobic liquid, which can let maybe some water, maybe some chemical mixture float on the surface, and also satisfy the evaporation rate, will it have the same phenomenon?
I chose to do water because I think it's a non-hydrophobic liquid, and I still wait till it to evaporate. So it's a really long time, but there's no fragmentation here.
Do you have other chemicals?
No.
Non-water.
I think all hydrophobic, non-hydrophobic liquids should be considered the same.
Moving on to the third question. Why does it fragment into smaller sizes?
As I said, I think the evaporate creates holes which gives it flows to fill.
Holes to give it flows, but as please turn here the video, please.
Yes, holes are right here, and it starts to into the inside.
Maybe the demonstration video.
That just observing the phenomenon, but it's not.
Look. There is no hole in this.
The thin layer.
I think you refer this middle drop as the mother droplet. So
yes, there's a thin layer of alcohol on the outside, which we cannot see clearly on this observation video. So this observation video is just telling us that this phenomenon does happen. So what I showed you is my experiment, which we can really
when you dispose it on the water, it just let me drop it. So I think when you dispose it on the water, it may form this shape, and you think that it will develop a hole here.
No. This droplet will separate into a thin layer of alcohol on the whole
How?
surface.
It's a mixture.
It's a mixture, but I think that there's a certain difference in the mixture. So maybe the alcohol tends to spread on the whole surface. And
How does the
alcohol
mechanism work?
is easy to evaporate. So if here there's something missing here, the others will try to fill in this hole.
So I think you will observe. You will maybe observe for the top view. For your explanation, this forms a thin layer, and there's some hole here. So
it did not spread on here. Here's the oil surface.
No. This is the thin layer.
Oh, yeah. And
Yeah.
this is the original droplet.
Yeah. So I think this refers to here, and this is here. So this forms a hole here. Then the liquid tries to in different direction to fill this hole. You will not observe this phenomenon.
We think it's in the same direction because, as I said, it will spread towards the inside or towards the outside. It should be considered the same, in my theory.
I'm curious about the fragmentation. So in the video, it has smaller droplet, which is also mentioned in the problem statement. So how does this smaller droplet form with your explanation of holes in this thin film?
I said that it brings towards the outside, and if
Can we draw, please?
so these original droplets will bring to the out. It spreads towards the outside, it will stay here. So then it will try to spread towards the outside in the linear swirling surface. And as I said, there's another kind of fragmentation which it comes to the outside and then spreads towards the inside. And there's bigger droplets on the outside. There's two reasons I just mentioned. I think maybe it's because the fragmentation process, or because there's a boundary of my pressure dish. So maybe here's extra force, like the surface tension make the oil a little bit higher. So these small droplets tend to collide into a bigger droplet.
So I think the limit of this your pressure dish is not mentioned in the problem statement. So I think you can improve this. Maybe
yes, I do agree. Trying a larger surface might changes the result.
So this is irrelevant to this effect. This petri dish is not mentioned in the problem statement. I think the main focus is on the burst.
That's a
of
part
this.
of my where my error comes from, and I do agree that we can improve in using a bigger dish or using a lower volume of our original droplet, which you just said that my volume of initial droplet is not considered. They are all 1 milliliter, so it's the same.
I can see in your video. So I'm moving on to the next question. So I can see in your video and try to have spike like this, and then fragment into smaller pieces. Yeah, the video. No, not this one. This is already fragmented.
Yeah, as I said, that's just observing the phenomenon, which is not our experiment. So we can't just investigate something other people do in their experiment. So I investigate what
Please turn to
happens
the problem
in
statement, please. Problem statement. Yeah. So this dispose may sometimes fragment into smaller droplets.
Yes.
Yeah. So I think you need to explain the mechanism of this, the formation of these smaller droplets.
As I said, there's full bring it up.
Okay. Moving on to the next question. So the droplet size is the droplet size is not uniform, right? You can see in your picture that the final droplet size is not those pictures. As you can see, there are a various size of the droplet. How can you determine what the size is?
We just use the average.
Average. How do you do the average?
Like in the middle, we consider the inner circle, and we just consider like 100 here, 100 outside, and we just do the average, which we can see here.
Do you know a software called ImageJ?
No.
Okay, so I think
So I can point out some specific ones and
I think
the average ones.
so ImageJ has a tool which you can analyze every particle size.
Yeah, I do agree if we're using that might improve
If you just choose some particular local size of the drop.
Yeah, I do agree if using considering every drop on the surface might improve our accuracy in our experiment, but we just do the average here, and we think it's already appropriate enough for us to see the difference between different concentrations.
Okay, so in the measurement, we have already talked about the Perry dish size, and moving on to the experiment. So in your page 4, so you mentioned that you put dye in it.
Yes.
I think it really affects the phenomenon, because when you change
there may be an error in there, but
when you change
because
the
we use a very low volume in our whole rate of our solution, so we think that we just ignore the small effects. But I do agree with you that we might put some accuracy. If we manage that, there might be more accuracy in our experiment.
So,
and as you said, there our temperature is
sorry, please. So in some modern studies, when you increase the concentration of maybe your alcohol or maybe the isopropyl alcohol, it changes the dissolve rate of the food coloring. So you cannot really quantify.
Yeah, I do agree there might be an error there, but I just think for the rate in our solution, it's small enough to be ignored. But we do agree with you that maybe we can consider that in different situations.
Okay, I think that's time. So I'll summary our discussion. So we talk about whether water mixture or hydrophobic liquid are necessary, and they respond that it's for all hydrophobic liquid will exert the same phenomenon, and we also talk about the fragmentation, and reporter answers that the holes will explain the phenomenon, but the opponent think that it's not the main reason, and the droplet size non-uniform. Opponents suggest for some software. We talk about dissolve, and we all in the fragmentation. We also discussed about some the effect of Perry dish size, which is irrelevant to this phenomenon, and for the experiment, let's discuss about the
die.
Thank you.
Okay, to the opponent, can you just slide 5, please? So this is a video. Slide 5, please. So slide 5 shows a video of the phenomenon. Is this your own video?
No. So this is just for the
Do you have
observation.
any citations for this video?
Here.
Okay, thank you. Thank you for citing that. It's good to clear out other people. My question is, in that video you have multiple drops. Did you also do multiple drops when you were testing the phenomenon?
Yes, as I said, I cannot consider that, so it's in the version.
How do you think doing multiple drops, like 1 drop, 2 drop, will affect the phenomenon?
Of course, the drop, like the second drop, will create an extra force towards the first drop, but
So did you account for this in your theory?
no.
Okay,
That might be an error.
Okay. So do you have a quantitative theory?
Excuse me.
Do you use like any numbers or actual like things you can plug in to determine your to validify your observations?
We think that there's too many forces to be
Okay,
considered.
so if you don't have a quantitative theory to describe it, could you think of any formula names or like equations you can apply to describe the situation?
Like Young-Laplace theory,
Okay.
we might consider that.
Anything else?
Uh,
Okay, now what variables would be present in your theory? Is the temperature affected? Was the velocity of the particle affected? The size of the particle? What variables would you think would affect the theory?
I think the concentration, and like in my key factors, I think the concentration, the kind of alcohol,
Okay,
and
thank you. Moving on to the reporter. So could you go to slide 27, please? Opponent, my bad. So you drew that diagram over there, right?
Yeah, yeah.
And look at how they say that the depth of the particle is uniform, of the fluid is uniform as you drop it in, but you drew something like a different gradient. So what are your thoughts on that?
I do not agree with this diagram. So as I know, surface tension wants to minimize its surface area. It will not form this rectangular shape. Yeah.
Okay, thank you. So how do you think that might occur? Why do you think that occurs?
The fragmentation.
No, that shape, specific shape.
Yeah, I just said that this is the result of surface
So
tension.
do you think the evaporation of the alcohol has anything to do with that, or anything else?
Yes. So it is a dynamic phenomenon. So
Okay, great. Thank you.
Yeah,
Can
yeah.
you describe to me what dissolve means? You just wrote dissolve, and what does that mean?
For the definition of hydrophobic, there is a extension to the dissolve rate. So for hydrophobic, there are many, little or small dissolve. Yeah.
Okay. For instance, you could test it. You could try testing it and then I would say you want to have a hydrophobic because hydrophobic it serves as the interface under the phenomenon to go further. So obviously, yes. So obviously, why would you test that? let me just add. So this is a problem statement, and the main focuses are what parameters affect the fragmentation of the droplets and what are the size of the final droplets. So this is what the reporter did. The reporter showed a video and explained the phenomenon using said video. However, there was no numerical analysis or quantitative theory of parameters which were explained. And they had no theory, basically. And they used different types of alcohols of different concentrations, but they didn't really have a lot of observations, and had little data. So some pros, it was clear. You showed your experiment. You suggested some parameters, and you had good visualization with your photos and videos. You don't mention a lot of variables because you have no theory, right? And there's large increments for the experimentation. Like there's not really testing between these increments. Again, no theory at all. I mean, numerical theory, quantitative theory, and you don't really explain the different results in your same data sets with your limited data, obviously. Yeah. And the opponent's performance, they summarized the presentation. They gave really good pros and cons. They asked pretty relevant questions and helped us understand the problem a bit further. But they did not mention some of the missed points, I'll get onto later. And they don't question they do question the accuracy of the report's results to some extent, but they don't really go further on that subject. And they don't refer to the lack of theory, which is really important when we're describing something. Okay, so I don't know time skip. They talked about the size of the particle. So the opponent asked how they determined the size of the particle and suggested that they could use a tracking software, image, something I don't remember, to consider the individual particles. And the reporter really just gave a really vague statement on how they described the size of the particle. They said they averaged, and they didn't really tell us how they tracked the particle. So I would agree with the opponent in saying you should use a tracking software to look at your particles so you can be more accurate with your data. And the opponent also asked if the hydrophobic liquid is necessary for the effect. Well, it's in the problem statement, so I think that we really should be testing with hydrophobic liquids. And moreover, the hydrophobic liquid will actually serve as a interface, fluid interface for the phenomenon to occur in the first place. Yeah, okay. And as of fragmentation, so the opponent said the process of fragmentation and individual particles should be discussed, while the reporter said the whole size provides enough data. In this scenario, in this case, I agree with the opponent, and that the fragmentation and individual particles should have been discussed more in depth because it's included in the problem statement. Some points that you missed. So the reporter lacked quantitative theory and a lot of data. Your data had large gaps in it, and the analysis really wasn't as accurate. And because of that, we didn't really have error analysis. And with no relevant or a lot of parameters to analyze, you didn't really have error in that case. And the opponent also brings up a good point about how you accounted for your petri dish when you could have used another dish, and that's really kind of relevant. Also, you didn't really mention the volume of the particle dropped. In your experimental process, you said you used 1 milliliter drop, but how would you determine that if you were dropping like from a syringe? That's a lot of error that you could have been accounted for. And those multiple drops, like you mentioned earlier, would also affect the spread of the phenomenon itself. And you also didn't mention the depth of the oil in your petri dish, and moreover, your gradient depth was also correctly incorrect. And you didn't mention how evaporation would play a role in the surface tension gradient and the depth of the fluid itself. Yeah, and that's about it. Thank you.
So for our concluding remarks, for some questions we want to discuss again, is that the water mixture and hydrophobic liquid is necessary? And we think yes, because it will affect the phenomenon like we just discussed. In fact of that, we agree that there might be an effect, so we can try not to use full coloring for future, just for observation. But we do use a very small amount of that, so we ignored it in our theory. So for the next question, for the final droplet size in our uniform, we agree using image J, which he said can consider all the droplets on the picture. So we might improve our analyzation. So we appreciate the advice. And next question is, how does the hole form? So we believe that the evaporation of a thin layer of alcohol we just discussed create the hole and trigger the hole effect. So the next question is thinking of the original droplet in page 27. So the picture is just demonstrating our theory, and we do agree there may be different shapes in 3D dimension, which may structure like this or like my picture shows, but we could not manage to consider it in our theory. And next is, are there any quantified results? We do agree that there may be a multiple number of equations can be considered, like with some of the theory might related to this experiment that we show here. But in our experiment, there are multiple of parameters or things we cannot manage to accurate or calculate. So we did not have a conclusion in our equation to predict what we should see, but we just do our experiment to observe what actually happened in the state. Thank you for listening.
Any question or story?
I have a small question for all of you. And I think that the reporter says that the water mixture will spread uniform on the surface, okay? But the reviewer or the opponent will say the water mixture will sink into the oil. So can you introduce an implemented setup that can observe some kind of the phenomenon? I mean, because I don't observe the real experiment. Yeah. So can you? Yeah.
So we did not. We do think there may be a 3D dimension, like it really sinks into, but we did not consider it here. But we do think that like experiment setup, we can use like lights to go through the structure and then put a paper at the back. So the shape of our droplets will be onto the paper. So I think that may help us to investigate this, but it's kind of complex. So
I like your experiment setup. I would like to propose a different experiment where you can, if you're simply thinking about the water droplet sinking into the hydrophobic fluid, you could simply create a really thin plane where we put, so it's clear, acrylic plane, where it's really thin, you put in your oil and you just drop your water into the plane, and you can clearly observe it go down because the water drops with a downward velocity as you drop it from up high.
I have a other experiment for basically you can analyze every droplet motion every time the depth of the liquid, which is you can shine a strong light on the liquid, and maybe if your light is strong enough, then the thin part will have interference. This interference you can see a chart called Michael-Levy chart, and you can observe the thin film interference and to see the chart and plot the real depth of the
Any other questions? If no grading time. For reporter, 8, 6, 6, 7, 5. For opponent, 8, 7, 7, 7, 6.
Thank you.
For reviewer, 7, 8, 8, 8, 7.
对对对，他练了。